Okay, so review
Oh, yeah. And
of electricity and magnetism. A few simple principles lead us to Maxwell's equations, which we don't solve as differential equations, but which give us a framework, and we see how everything relates. So the first thing we have to understand, and this is actually okay, Coulombs Law. Now we know what's the R vector?
the distance from your charges.
It's what now?
The distance.
It's a vector.
A vector is not a distance. This is a distance.
A vector from one charge to the other.
Yeah,
Or
vector from one charge to the other, right? Depends which charge is which. And if it's F12, then it'd be R12,
That's cool.
okay? And the R's are magnitudes of R12, okay? So we know how to use that, and make sure you do, okay? Make sure that what you get makes sense when you plug in two charges and the vector between their positions, right? Make sure the vector's in the right direction and the notation is all consistent. And then if you have superposition, okay? Could be expressed as F equals I don't have a good notation for that. I'll say F sub n equals F1n plus F2n plus Fn minus 1n. All this is saying is that if you have a bunch of charges, the force on one of them is the sum of the forces exerted on it by all the others. Okay? And that's superposition. And of course, if you have a charge distribution, then this becomes an integral. Okay, so electric field is defined as the force exerted by the charge distribution on Q divided by Q. Okay? Electrostatic force on charge Q is the field. Okay? Potential difference, we'll call it VAB. Is the work per unit charge from A to B. Now I'm giving you a complete definition would say whether that's the work on the charge, okay, or whatever, and you know the path from A to B and so forth. So I'm just giving you a brief idea of what these things are rather than getting into the details of the definitions, which you can sort out in solving problems, okay? So there's your potential difference. It's a work per unit charge from A to B. There's some details. I'll just say add details. It's not a detailed definition. Okay, but that's the idea. Work per unit of charge, right? So we can write it like this. In the application, of course, you have to be careful about those details that I'm not mentioning right now. Okay? So we've got force on a collection of charges, and you can then write this as an integral. Okay? Electric field, potential difference, and potential difference is generally a line integral. Although there are limits on the kind of line integrals that I can ask you to do in this course, because the prerequisite is just a year of calculus, and you don't do line integrals in the first year of calculus, but everybody knows line integrals, and it just helps you understand the whole concept of potential difference if you know what a line integral is and how it applies in this situation. Okay? So, we have that. Now, what else do we have? Well, the flux of the electric field, okay? And it's basically I'll say E perpendicular times A, where A is an area, and E perpendicular is the component of the electric field perpendicular to that area, right? Now, more formally, because you know the multivariable calculus, it's the integral over the surface of E dot n ds, where n is normal to the area increment. Okay? And actually, it's E dot, let me write it better, it's, I'm going to fix this. It's a double integral of E dot ds, and by that I mean the double integral of E dot n dA, which is, and this is a surface integral, okay? So your picture is simply that if you've got a surface, surface here with a surface element here and a normal vector, so there's a surface with an area increment in a normal vector at some point on the surface. Then if you have an electric field, the flux is just E dot n times the area, right? And E dot n, if this is n, and this is E, I didn't say unit, but this is a unit normal vector. So E dot n, as we know, is just this. Right? Get your angle here. E dot n is just this, and I didn't leave myself a good place to label that. But I'll use a different color here. E dot N is just this side of the triangle, although you gotta be careful because it could be negative. Could you get an inward flux or an outward flux, right? So, okay, so that's the idea of flux, and if you have a magnetic field, the picture is exactly the same, except it's a magnetic field. Everything is, you got a B here and a B dot N dA here, okay? You don't have to actually do the flux integral, because again, it's multivariable calculus, but you know how. So hopefully that helps you understand.